Chapter 9, Modeling Our World. Now, this chapter, it kind of takes some of the concepts we've learned this semester, but also some concepts you may have learned from previous math courses, and shows you how you can use mathematics to model our world, basically describe your world through mathematics. Um, as you've seen, most of our class involves finances. And so this next section will also help us use mathematical modeling to help us in our financial decisions. Let's start with the easiest, one of the easiest forms of modeling that's known as linear modeling. Now, in linear modeling, you'll notice that you have what are called linear functions. And a linear function has a constant rate of change, and they usually, usually can be represented pretty easily, just simply by using a straight line graph. Now, the rate of change is equal to the slope of the graph. And the slope, again, you probably have some experience with that, and we'll talk about slope in a moment. But the greater the rate, the steeper the slope becomes. Now, the rate could be in the positive direction, or it could be in the negative direction. But the point is that you could actually have a very high rate of change that is positive, or a very high rate of change that is negative. And the greater the rate of change, the steeper the slope becomes. Now, calculating the slope is going to be important in this section, so it'll be important for you to see how we calculate the slope. Again, this is probably something you've seen before. In fact, if I could put it in terms of a typical algebra class, basically you just take the y values, you subtract those, and you divide it over the difference in x values, usually. But the more general way of stating it is right here. It's the change in dependent variables divided by the change in independent variables. So finding the slope of a line is going to be actually kind of important. You basically look at any 2 points and divide the change in the dependent variable by the change in the independent variable. And essentially you look at any 2 points. As you can see here, I have point 1 and point 2. And you want to essentially judge the steepness of your slope and also the slope itself by looking at how high it rises or how low it falls. That would be the change in dependent variable. And you'll divide that by the change in independent variable. Now that's very important to point out because, again, the change in the dependent variable must be in the numerator. The change in the independent variable must be in the denominator. So please keep that in mind as we move forward. I'll go ahead and show you like a nice example of how this works. So for example, let's say we had a small store and sold fresh pineapples. Now, based on the data for pineapple prices between $2 and $5, the store owners created a model for which a linear function is used to describe how demand varies with price. Now, you'll see in a moment, I'll show you a picture, but I think we all can understand. Let's say a particular store sold pineapples for $2 each. Well, pretty easy to see that if you sell $2, that's a pretty good price for pineapples. This store sold 80 pineapples at $2 a piece. Okay. Now, what do we think is going to happen? Just, what do we think is going to happen if the price gets increased to $5? So obviously at $2 a piece, it's a pretty good price for pineapples. They sell 80 of them. Now it depends on how big the store is. That could be a lot of pineapples. That might not be that many, but let's assume it's a small store. So 80 pineapples is actually pretty good. So once again, I ask you, if they sell them at $2 a piece, they sell 80 pineapples. But what if they increase the price to $5 all of a sudden? Well, obviously, people still probably want their pineapples, but there's going to be a lot less people wanting those pineapples, right? So taking a look at this picture here, if you'll notice, here again, we have our graph. Okay, down here is the price of pineapples in dollars. So again, we started off with $2 here, right? So let's draw an arrow straight up to here. Okay, and that gives us this point up here. Yes. But then for some reason, whether it be the economy or who knows why, the store owner decides to increase the price from $2 up to $5. And so obviously, because they increased the price from $2 to $5, the number of pineapples, the demand, obviously decreases. As we're going left to right, you'll notice this line is going downward, right? And in this particular model, notice that when they increased the price to $5, they still sold a good number of pineapples. They sold 50 pineapples, but obviously, it makes sense, right? It's less. So again, point one, $2 created 80 pineapples sold, whereas $5 caused there to be 50 pineapples sold, so less demand, less desire for pineapples once the price goes up. Now, what's that change in demand? Now, remember, you want to calculate the dependent variable first. You want to calculate typically whatever's on this y-axis here first. So we get the change of demand is 50 minus 80. Okay? 50 minus 80. Now you might wonder, well, how come it's not 80 minus 50? Well, it's always going to be the latter minus the former. So it's always going to be what happened after the change minus what happened before the change. So 50 pineapples occurred after the change when it was raised to $5 minus the former, which is 80 before the change. And notice that our change is negative 30, created a negative demand. So the demand decreased from point 1 to point 2. So notice that our change in demand is negative. That's actually very important. Okay. So you might have, again, noticed that, as I said, you didn't see the number 3 or $3 on the previous slide. Well, that's because it is there, but you'll notice that the store owner increased the price from $2 to $3. That is to say $2 to $5. The difference between $2 and $5 is obviously $3. So that's where the $3 comes into play. And we obviously already saw that the change in demand was 30 less pineapples. This can be reduced down to negative 10 over $1. So what does this mean? Our conclusion is what? For every dollar that the price increases, 10 less pineapples are sold. Now, one good thing about rate of change is it allows us to calculate change in the dependent variable from the change in the variable of independent value. Excuse me. Now, really, what you're about to see is just simply a rearrangement of the slope formula. If you simply multiply both sides by the change in the independent variable, you actually do get the change in dependent variable. So here's the formula for if you are asked in the homework to find the change in the dependent variable. So go ahead, pause the video, write this down, to have this ready for you when you're taking doing the homework. But essentially, if we look at that same graph from before, let's go ahead and use linear demand function below to predict the change in demand for the pineapple if the price increases by $3. It's pretty simple. All we simply have to do is recognize what's our independent variable. Again, it's the price of the pineapples. What that means is the demand for pineapples completely depends on the price for the pineapple. So obviously, it's not the other way around. So it's not like, demand dictates price. It's the other way around. It's price dictates demand. And once again, the rate of change of demand with respect to price is -10. So let's go ahead and take that formula we saw from the previous slide or 2 slides ago. And essentially, you just go ahead and replace the rate of change is -10. We got that from a few slides ago. That's this right here. And the change of price, well, again, the store owners decided to increase the price by $3. That's why it went down 10. So that gave us -30 pineapples, which is what we saw previously, as predicted. And that's the beauty part of linear models. They're very predictable. Okay, another formula that you should know is the formula for the dependent variable itself. And how do you find the dependent variable? You basically take the initial value and you add it to the rate of change times the independent variable. Now, unknowingly, this is actually something you've probably seen before many times. In fact, I'll go ahead and show you what this actually ends up being, and I'll repeat myself later. And you've probably seen this before. In fact, here's a better way to look at it. And this should look very familiar to you. You've probably seen this before in a typical algebra class. So hopefully many of you have seen this. And essentially, this is what you just saw, what is the algebraic equation of a line. In algebra, x is commonly used for the independent variable, y is used for the dependent variable, and usually for a straight line, slope is indicated by the letter m, usually. Okay. And the initial value, or y-intercept, is denoted by the letter b. And again, you've probably seen this before. Once again, you see this formula here, y equals mx plus b. So let's just take a look at a typical line. So for example, this line here, this equation, we have the line here, y equals 4x minus 4. Right? Well, okay, in this particular case, you'll notice that a few things are happening here. Well, number one, the slope here, it's a change, right? It's the change in dependent variable, that's the 4, divided by the change in independent variable. Well, we all know 4 divided by 1 is just simply 4. So that's how we got the 4 here. And the y-intercept is always going to be where the line crosses the y-axis down here. So notice how in this particular case the line crosses the y-axis at -4, which gives us all the parts that we need for our equation of a line, which is y equals 4x minus 4. And again, this hopefully is something you've seen before and should not be too surprising to you. But the different parts of a slope are also just as important, so let's go and take a look here. Let's talk about different various slopes. Now, earlier we saw a slope that went down as the pineapple prices increased. We started up here, and then as the pineapple prices increased, demand drug us down, downward. Because obviously, the higher the price, the less we want to buy pineapples, right? So this black line here represents what's known as a negative slope. The other line here is a positive slope, because as you'll notice, we start low, and then as we move to the right, we actually end up getting higher and higher and higher. And that's really the key. As you move left to right, is the key. Are you going up or are you going down? So again, this red line here, we're going up as we move left to right. That would be a positive slope. That's right here. As we're moving left to right, are we going down? That would be a negative slope. But then finally, if you take a look at, as we move left to right, take a look at this third line here in the middle, the blue line. Notice how this line here, I can start here, and as I move from left to right, there's no change. I don't go up and I don't go down. Well, that means you have a slope of 0, which gives you a nice horizontal line. Now, what if we have 3 different lines that have the same slope? Notice that these are all, each one of these points are going up at the same rate of change. So this line here is a positive slope, right? Okay, but you'll notice that B is also positive. Well, that's because the y-intercept is above the x-axis. However, if I slide this line down to here, you'll notice that B equals to 0. Well, that's because here B is at the origin. The y-intercept's at the origin. And then here, B is negative. Well, that's because, my y-intercept is below the x-axis. So again, in this particular case, I'm not really too concerned about the slope because the slope for each one of these is the same. You'll notice that they're all parallel to each other. But you'll notice that they all have different y-intercepts. So as you can see, if you vary the slope or you vary the y-intercept, you do get different lines. So those are actually important to notice and keep in mind. As an illustration to this, let's go ahead and take a look at this example. Now, what we want to do here is we're going to go ahead and use the function here on the right to write an equation that describes the rain depth at any time after the storm began. Now, there's a couple things I want to point out here. Let's take a look at the slope here. Slope, again, is change in the y direction. That's here, 0.5. Okay. Change in the y direction divided by change in the x direction. So you'll notice it's up here. Change in the y direction divided by change in the x direction. So 0.5 divided by 1 is just simply 0.5 inches per hour. So that's going to be our slope. Slope is going to be 0.5 in this case. And notice also that the y-intercept crosses here at the origin. So because of this, we actually end up getting a function of r equals 0.5t. Now you might be wondering, wait a second, I'm used to seeing y equals mx plus b. Well, just understand that you can use any variables you want. Just in this case, r happens to be our y variable, our dependent variable, and t here happens to be our independent variable. And then I could, I guess, suppose add a plus 0 to this for my y-intercept, but that's not necessary. And the question also says, use this equation to find the depth 4 hours after the storm began. Well, all I simply do is replace t here with a 4. Notice I have 0.5 times 4. That gives us 2 inches. Is the second answer here. So a pretty straightforward linear model, in this case, dealing with rain depth. Now you can also use linear functions to form 2 data points that help you find slope and help you also determine rate of change. Once again, let's go ahead and just kind of like outline what you do. So if you're ever given 2 points, remember, you can easily find the slope by first subtracting the y values, again, the dependent variable, and dividing it by the difference in x values, the independent variable. Once you figure this out, again, whatever you get out of this is going to equal to m, your slope. And once you find that, go ahead and substitute that slope that you got from step 1 into this equation right here. Now, not only that, what you also want to do is plug in not only the slope here, m, but you're also going to want to plug in whatever points they gave you as values for y and x. And once you do that, you're going to be able to actually solve for the y-intercept b, and you'll pretty much have everything you need. Because once you have your slope and your y-intercept b, you now finally have your equation of the linear model, which once again is y equals mx plus b. So as a last example to kind of help us understand, until about 1850, humans used so little crude oil, we can basically call that amount zero. It wasn't really discovered as that resourceful quite yet. Maybe, I mean, it was very resourceful in things like, lighting, putting lanterns that last more than what a candle would last. Also, there's several things that oil was used for, but it was so small of a use because cars weren't invented yet that by comparison to now, we can basically say that in 1850 we used zero crude oil. Now by 1960, humans used a total of 60 billion cubic meters of oil, which is insane amounts of oil, and by now it's got to be even more than that. So let's create a linear model that describes the world oil use since 1850. Now, before I even get into this too much, let's take a look at 1850. Now, in 1850, that's the independent variable because we are depending on the year to understand how much oil was used, right? Not the other way around. We depend on the year to ascertain how much oil was used, right? So I think it's fair to say that our first point is going to be 1850 represents our independent year, and because of the year, we are using basically no oil at all. That said, now we go ahead and look at what's going on in 1960. So that gives us our second point. And our second point, again, being the independent year, 1960, and our dependence in oil obviously increased by quite a bit. Remember, this is 600 billion. This is in billion cubic meters. And I can only imagine what it is now. So I'll go ahead and rewrite that again here, or type that anyway. So let's go ahead and find the slope. So again, how do we find the slope? Again, it has to be the difference in dependent variables divided by the difference in independent variables. So again, notice how these numbers I circled here, 600 minus 0, those go on the top. And then 1960 minus 1850 goes in the bottom. Now, one other thing to point out when it comes to this particular problem, one more thing to point out, is that the 600 and the 1960, notice how they're right on top of each other. Well, that's because they go together, and that's very important. And in similar fashion, notice how the 0 and the 1850 are right on top of each other. That's no coincidence. So please make sure that you are staying consistent. And we end up, in this case, getting 600 divided by 110. 600 divided by 110, just throw that in the calculator, you get 5.45 billion cubic meters per year. So every year that we went from 1850 to 1960, we increased by 5.45 billion cubic meters per year. So, okay, we go ahead and plug that into our formula here. Well, this is going to be our slope. Okay, and I know we're used to seeing x here, but we'll use t for time. It's okay. You can use whatever variables you want. Okay, so once again, I'm going to go ahead and plug in this. Now we're going to go ahead and find b. Now, it's pretty easy to find b. Some of you guys with some experience with b in this case will know what b is going to be already. But essentially what you do is you go ahead to find b. You take one of these points, and actually you can use either one of these points. You can use really either point up here. Okay, either this point or the other. But this to me is the easier point because we have 0. And anytime you can use 0, it's always a nicer situation. So what you simply do is you replace M with 5.45, which I did, and you replace the time, 1850. So watch where that goes. That's going to go here. Okay? And also our 0, that's our dependent variable, is going to go here. So I'm just going to basically plug in these values into that function to give me this. And notice I don't know what B is yet. Well, I will know very soon, because all you simply do is multiply 5.45 times 1850. That's going to give us negative 10,083. Once you solve for it. And thus I can go ahead and put it into my equation, which gives us this as my function. And essentially, you can get a linear function. But here's the thing, though. Does this really truly describe our oil use from 1850 to now? And then actually, the answer to that is no, it doesn't. It doesn't, because we went from 0 to 600 billion cubic meters within the span of 100 years. And it's probably even more than that now. So what I'm going to talk about in the future is we got to actually look at different kinds of models. So this is actually an example of where linear models is not sufficient. We really need to look at what's known as exponential models. And that's not this section, but we'll talk about that momentarily. So this red line here, the red line right here, is what we just figured out. So that red line is what we figured out in the different slide. But if we're being honest, this exponential curve is what we're really looking at. From 1850 to now, our oil use has not just gone up linearly, it has skyrocketed. And we'll be talking more about that kind of model in the future. But for now, we'll stick to linear, keep it kind of simple, and exponential is coming up next.